Hello, everybody. My name is Rick Frage, Sales Manager at SFTec Canada. Thank you for joining this webinar titled Design of Flat Plates Using GFRP, Glass Fiber Reinforced Polymer. Today, the first of many, actually, the first of many webinars of about different subjects that we're planning to do in the coming weeks. So this webinar is supposed to take about 45 to 50 minutes, and we're leaving about 10-15 minutes at the end for questions and answers. Before we start, I would like to introduce Dr. Ahmed Salama. So Dr. Ahmed Salama is our head of technical department at SFT Canada. Dr. Ahmed has earned his Bachelor's of Engineering and Master's degree in Structural Engineering from the University of Cairo in Egypt. He worked for the Egyptian Ministry of Water and contributed to several projects during his employment there, like the Al Sharika Bridges project and the Ismailia Canal project. He then came to Quebec after being admitted to the PhD program at the University of Sherbrooke to continue his studies in structural engineering under the supervision of Professor Brahim bin Mukran. He specialized in concrete structures that are reinforced with fiber reinforced polymer. So basically, he's the right guy to learn about how to design reinforced concrete with fiber reinforced polymers. He joined SFTec in July 2019 as the head of the technical department, where he worked on several projects in different industries. He worked on telecommunication towers, water purification stations, different slab projects, ICF walls, and many more. So if you have any questions towards the end, I believe he is the right person to pick his mind. So I'll give him the mic to talk, and I hope you enjoyed the presentation.
Yes, so thank you so much, Rick, for this great introduction. Do you hear me well? Rick?
Yes.
Okay. Thanks a lot, Rick, for this great introduction. I highly appreciate it. So again, welcome to all of you from different parts of the world and different time zones. This gives me pleasure to see a really good presence in our webinar. Please stay with us and we all will learn together. Today we are going to talk about design of flat plates using glass fiber reinforced polymer bars. In the next slides, I will go through brief introduction, field applications with FRP bars, design of FRP-RC flat plates, and finally I will give some concluding remarks on the presented slide. In the beginning, I would like to introduce our company, SFTec. SFTec is a professional entrepreneurial industry in the business of composite rebar. What do we do and who do we work with? SFTec is working closely with national and international consulting firms and government departments in the construction of parking facilities, water treatment plants, retaining walls, and other infrastructures. What is our focus? SFTec is focusing on the market of FRP rebar applications in North America and beyond through providing a complete design for new structures reinforced with FRP rebars. Conducting research and development strategies to ensure continuous improvement of SFTec products. So, the question now, what is the composition of FRP materials? As per the microscopic analysis on our right side, FRP materials consists of fibers, polymer matrix, and the interface between the fiber and polymer matrix. FRP materials may be bars or sheets. We are using FRP bars as a creative solution to eliminate steel corrosion problems in many infrastructure located in the northern climates. While FRP sheets for strengthening and rehabilitation purposes. In our presentation, I will focus on FRP bars. So, what are the types of FRB bars? In the market, we have three main types: carbon fiber, armate fiber, glass fiber, and recently we have a type called basalt FRB bar. However, GFRB bars have recently gained a wide acceptance as a practical construction material for sustainable new constructions due to their cost effectiveness than other types of FRB. As we see here, the typical stress strain curve for steel and FRB. There is only difference between steel and FRB bars is that FRB are linear up to failure and exhibit no ductility or yielding. In our company, we are focusing on the production of GFRB material as straight bars, bent bars, closed loops, and spirals. And also we have another type of GFRB materials called GFRB shear connectors for sandwich panels. Why you must use GFRB bars instead of steel bars? In the last 10 years, the FRB bars have been used successfully in hundreds of bridges, parking facilities, tanks, marine structures across Canada and US. FRB materials offer many advantages over the conventional steel bars. Longer service life, improved durability in harsh marine environment, the advantage of corrosion resistance, high tensile strength compared to the yield strength of steel, no corrosion even in harsh chemical environment, and finally, neutrality disturbance. So, SFTec products versus existing standards. Really, our products go through strict testing requirements before they are approved for the market as a cost-effective reinforcing material instead of corrosive steel bars. The bar satisfies the minimum requirements of the specification for fiber reinforced polymer code CSA-S807 to the year 2019. The bars also satisfy the minimum requirement of the Ontario Ministry of Transportation classification to be considered for infrastructures work in Ontario province. The FRB bars testing are classified into three categories: physical properties test, mechanical properties test, and finally durability test. As an example, I will give you a detailed information on mechanical properties requirement for the Canadian standard S807, the MTO classification versus SFT bar. This table presents the mechanical properties for grade number 3 GFRB bars of size number 6. Size number 6 here means 20 millimeter. As we see here in the first row, the tensile strength of SFT bar exceeds the minimum requirement of the Canadian standard S807 and MTO by 60% on average. The elastic modulus of SFT bar exceeds the minimum requirement of the Canadian standard S807 and MTO by 8% on average, as we see here in the second row. Also, for the minimum transverse shear strength, minimum bond strength, and the minimum strain, our materials also exceed the minimum requirement by the Canadian standard S807 and MTO. I would like to highlight on our national and international projects with FRB bars. The first application we have here is the first worldwide waffle slabs reinforced with GFRB straight and bent bars, as we see here in this photos. Another example here for shear walls at Shandong subways in China. Another application for casting water breaks using our GFRB bars. Finally, we have another great field application with our GFRB shear connectors in precast sandwich panels at one of IBM buildings. I will shift now to another field applications across North America. These photos represent a project with Hydro-Quebec for precast GFRP chamber. In this project, the steel bars have been replaced with GFRP, having the same diameter, reinforcement configuration, and then tested to determine the strength and behavior compared to the steel one. The test results reveal that the capacity of the GFRP chamber is almost the same as with the steel as with the one with steel bars. We can conclude that the design of this chamber is approved by testing, not by design. One of the most important applications also is the construction of water treatment plant using GFRP bars as we see in this photo, in order to resist steel corrosion in such chemical environment. In these photos, we can see another example for the preparation and installation of FRP bars in retaining reinforced concrete walls for Eel River. These photos represent the demolition of the deteriorated slabs as we see on our left side in the rear parking garage. On the right side, we can see the complete replacement of these slabs using GFRP bars. The last field application we have today is on flat plate structure of Le Chancelier parking garage in Quebec City. As shown in these photos, the flooring slabs of this two-way parking garage totally reinforced with GFRP bars. I would like to shed the light on the story of this application. In year 2011, deterioration was observed in Le Chancelier parking garage at Quebec City. Mandated engineering firms decided reconstructing the deteriorated slabs using GFRP bars, which would be more economical than repair and maintenance. Before proceeding in the construction of this project, a collaborative project between the University of Sherbrooke and MTQ, was initiated to implement GFRP bars in the Chancelier parking garage. This application was in service since 2011. Now I will shift to the design of FRP-RC flat plates using GFRP bars. Before starting this point, we need to highlight the problems in such structures. All of us know that flat plate structure provide architectural flexibility, more clear space, easier formwork, and shorter construction time. However, we have two major problems. The first problem we have is the corrosion problem, as usual in many parking garages located in northern climates. We learned together that the solution is to replace the corroded steel bars with GFRP bars. The question now, are we going to follow the flexural design philosophy and procedure as with the steel bars? The answer is yes. We will use the flexural theory and procedure as in steel, but after adapting this equation to include the mechanical properties of FRP bars instead of steel. These equations are existing now in the recently published FRP codes and design guidelines in North America and others all over the world. In the next slides, we will learn how to do that in detail. In spite of flat plate advantages, their connections are susceptible to bunching shear failure. And it is the second problem. The problem number one is the corrosion. Problem number two is the bunching shear problem. Typically, the bunching shear failure takes place when excessive gravity loads transmitted from the slab into supporting columns. So the area around the column is too heavy and just fall right through. And the area around the column is unable to resist it. As shown in these photos, photo number one on our left side is for Montreal parking garage. The bunching shear failure is very clear here around the column. And also on our right side, we have a photo for Bibber's Row parking garage. The bunching shear failure also is clear here, as you see around this red circle. Okay, so it is worth mentioning that several codes and guidelines are available around the world for design of a structural element reinforced with FRB bars. As we see here, we have two main codes in Canada, two main codes in US. In Canada, we have the Canadian standard S806 for structural elements reinforced with FRB bars, and we have CSA-S6 for bridges reinforced with FRB bars, and we have two alternative codes like the CS806 and the S6 in the US, ACI 440 and the ASH2 LRFD, and also we have in Japan the Japanese standard series number 23. In Europe, we have bulletin number 40. There are some general issues should be considered in the flexural design of any structural member reinforced with FRB bars. I will talk here on these issues according to the Canadian standard S806 to the year 2012. There are three possible modes of failure for concrete section reinforced with FRB bars. The first one is balanced failure, which represents simultaneous rupture of FRB bars and concrete crashing. The second one, tension failure, which represents FRB bars rupture before crashing of concrete. The third one is compression failure, which represents the concrete crashing while FRB remains in the elastic range with a strain level smaller than the ultimate strain. Issue number two. There is a difference between steel and FRB is that FRB are linear up to failure and exhibit no ductility or yielding. Another major difference is that serviceability will be more of a design limitation in FRB reinforced members than with steel. Due to the lower elastic modulus of FRB bars, deflection and crack widths will govern the design. Load factors and load combination. The Canadian standard S806 uses the same load factor as in the Canadian standard A23.3 to the year 2014 for steel structures. Load combinations are also the same as in the Canadian standard A23.3, which are based on the National Building Code of Canada. Material resistance factors. The concrete and steel resistance factor remains the same as in the Canadian standard A23.3 the year 2014, while FRB resistance factor equals 0.75 for all FRB structures, reinforced or pre-stressed. In this slide, we have a design example for a prototype flat plate parking garage with 5 by 5 square panels. As we see here, we have equal 4 panels in each direction. The slab thickness is 200 millimeters. All columns measured 300 by 300. FC dash equals 40 MPa. The requirement. The first thing we will do, we are going to design this flat plate for flexion. The second one, we will check the bunching shear capacity at the central column. As we see here, we have 1, 2, 3, 4, 5. We have 5 columns here and 5 columns here. We select the central one. This one, all of us know this one is subjected to a concentric bunching shear because it's central. The first step in the flexural design is to calculate the ultimate load. As I mentioned in the general issues, the loads are specified in the Canadian standard S806 according to the National Building Code of Canada. We are going to calculate the service load and then ultimate loads. The dead loads is simply the weight of the concrete plus the partitions. The weight of the concrete equals the density of concrete, which is 24 kilonewton per meter cube, by the slab thickness. We have a slab thickness of 200 millimeters, so zero point 0.2 meter. Plus the partitions. The partitions in parking garages, according to NBCC to the year 2015, equals 1. So finally we have W dead load 5.8. The life load also is taken 2.4 according to NBCC 2015 for parking garages. So finally we have WS, which is W dead load plus W live load. So finally we have 8.2. So again, the ultimate load. The ultimate load is the maximum of 1.4 dead load or 1.25 dead load plus 1.5 live load. So we will take the maximum of these two values. Here we have 8.12 and 10.85. So the ultimate factored load is 10.85. The second step in the flexural design is to estimate the straining actions on the floor as the negative, positive moments, and shear forces. All of us are excellent and can do that using any finite element program like SAP or SAFE. Now we will consider that we have the value of the factor, the negative and the positive moment. So the next step, we need to estimate the amount of FRB bar. All sections are preferable to be designed as a compression control, as per the Canadian standard S806. The over-reinforced section or compression controlled section means that the row greater than row balanced. So the amount of reinforcement and should be greater than the balanced flexural reinforcement. So now we have the M resistance from this equation. We have M factored from the analysis. So we will compare the M resistance by 1.5 M factor. So M resistance should be greater than 1.5 M factor. If you will go and design this one using this equation, you will get the flexural reinforcement ratio of 1%. Also in our design, we should satisfy the minimum reinforcement ratio, which is 400 times the elastic modulus over the area gross. And this term should be greater than 0.0025 area gross. To have a good design with FRB, and especially I'm talking with FRB, you should check the serviceability limit state in such structures. The modulus of elasticity of FRB is lower than that of steel. So the higher strength cannot be fully utilized in reinforced concrete structures. I here mean the case of the over-reinforced section. So we are not going to use the full strength of the bar. Okay? Hence, the design is mainly to control the crack width and the deflection. In order to do that, we have two checks. The first check here is the check for the maximum stress under service load using this equation according to the Canadian standard. So the first check we are going to do to get the maximum stress under service load. The code allowed using 25% of the ultimate strength of the used FRB bar. So let us say we have the ultimate strength of the used FRB bar 1200. So we will compare 0.25 by 1200 to the maximum stress under service load. Now we check the stress in the used reinforcement, and the elastic modulus is known for us. So we have here the maximum stress in the FRB bar under service load. We know the elastic modulus from the manufacturer or from testing, so we can get the ultimate strain under service load. When the maximum strain in the FRB bar under service load exceeds 0.015, the crack width parameter should be verified. We have a parameter called Z. Okay, so we can check Z from this equation. The value of Z should be less than 45,000 Newton per millimeter for interior exposure and 38,000 Newton per millimeter for exterior exposure. In the case of designing flat blade parking garages, sections should satisfy the 38,000 Newton per millimeter criteria. We did the required checks, so I will shift to another important part for bunching shear. Let's take a look how we can check the bunching shear of the selected column C8. We can do that actually using the Canadian standard S806. Again, all columns measured 300 by 300 millimeter. The effective slab depth equals 160 millimeter. The ultimate factored load equals 10.85 as calculated before. The first thing we need to do is to find the critical shear area. The critical shear area is simply located at d over 2 from each column face around the column. As we see here, we have the column C by C, 300 by 300. So how to locate the critical shear area? You will go d over 2 from this side and d over 2 from this side, d over 2 from this side and d over 2 from this side. So the side length of the square column equals 300, d equals 160. So the side lengths of the critical shear area equals 460 millimeter by 460 millimeter. So we need now to find the tributary area. That is like the force that pushing down and going to separate the critical shear area from the rest of the slab. Okay, let's draw it. What is this area here? The dimension is simply half the length between columns. We have here 5 meters, so in this side we have 2.5, and we have here 5 meters, so we'll go 2.5. In the other direction, we have 5 meters, so we'll go 2.5, and we have here 5 meters, so we'll go 2.5. This length is going 5 by 5, as we see here on our left side. So the tributary area, I'm going to shade this area here. This area that I have shaded in is the tributary area. We have to subtract the outer area from the inner area to get the area of tributary area. So the area of tributary area equals 5 by 5, 5 by 5 minus 0.46 by 0.46. So the tributary area is 24.8. The area of tributary area is 24.8 as calculated before. The ultimate factored load is actually acting on this area. The WF times the area of this tributary area can give us the ultimate bunching shear force. So the next step is to calculate the ultimate factored shear stress. But first, let us calculate the ultimate bunching shear force. So the ultimate bunching shear force is simply the ultimate factored load times the tributary area. Before going to calculate the bunching shear stress, we need to estimate the bunching shear perimeter. The bunching shear perimeter is simply the summation of the side lengths of the critical shear area. So we have here 4 sides with 460 millimeter length. So we have 4 by 460 millimeter. The ultimate factored shear stress is simply the ultimate bunching shear force over B node by D. We have D 160, we have B node 1840. So finally we have the ultimate bunching shear stress 0.91. The ultimate factor shear stress is known for us now. The next step is to compare it with the allowable bunching shear strength to check is it safe or not. The bunching shear strength is the least value from these three equations. We have three equations according to the Canadian standard S806. These equations are essentially the Canadian standard 23.3 equation with modifications to account the FRB bars instead of steel. In these equations, we have new terms that should be determined, like alpha S. Alpha S is a factor depends on the column location. We have here interior column, so alpha S equals 4. Beta C. Beta C is the ratio between the longer side of the column to the shorter side of the column. EF. EF is the elastic modulus of the FRB bar. Let us say we are using soft bar with 65 MPa. Rho equals 1% from the design. Lambda is a factor depends on the concrete strength. Lambda equals 1 for the normal strength concrete. The concrete resistance factors equals 0.65. We know from the beginning, that the concrete strength is 40 MPa and the depth, the flexural depth is 160 millimeter. Using these numerical values, in this equation, we get three different values for the allowable bunching shear stresses. We have here the lowest one is 1 MPa. So the allowable bunching shear stress is 1 MPa, and the ultimate bunching shear stress is calculated before 0.91. By comparing the allowable and the ultimate values, the connection is safe and no need to add transverse shear reinforcement. But if we have the inverse, we need to add shear reinforcement because it will give us unsafe design. In this step, I would like to show how we can use the American guideline ACI 440 for calculating the allowable bunching shear stresses. It is worth mentioning that the ACI 440 to the year 2015 using the same concept as in the Canadian standard S806 in calculating the ultimate factor shear stress. So as I explained before, the VF calculation method, it is the same in the ACI 440. The ACI 440 is using only one equation, as we see here, this simple equation for calculating the allowable bunching shear stress. This equation is mainly depending on two factors only. We have factor called K and FC dash. K can be calculated using this equation. The K equation depends on two factors, the rho, the flexural reinforcement ratio, and the modular ratio. The modular ratio is the ratio between the elastic modulus of the used FRB bars to the elastic modulus of concrete. So we can calculate rho by NF. After calculating rho by NF, K can be simply calculated and it is equal 0.189. And finally, the allowable bunching shear strength times the phi factor equals 0.7. The phi factor for shear equals 0.75 according to the Canadian standard, according to the ACI 440. As we see here, the comparison between the allowable and the ultimate bunching shear stress yielded unsafe design, and the transverse shear reinforcement is needed. So we compared VF by VC. VC is zero point 0.7 and VF 0.91 as I explained before. So here we have unsafe design and we need to add transverse shear reinforcement. It should be noted that the experimental evidence in many research studies revealed that the ACI 440 equation is unsafe for design. But why? Because this equation considers the flexural reinforcement ratio only and ignoring the FRB axial stiffness. What is the meaning of FRB axial stiffness? The FRB axial stiffness is simply the rho F times the EF. So it dropped this factor from the equation. I highly recommend using the Canadian standard equation instead of the ACI in bunching shear design. This is my opinion. And if you go and read any publication on bunching shear behavior for flat plate structures reinforced with FRB bars, you will see this. Based on the presented slides, the following concluding remarks can be drawn. Number one, safety rebar is a very good solution to reinforce concrete infrastructure located in harsh environment. Number two, FRB bars have been used successfully in hundreds of bridges, parking garages, pavement, piles, and foundations across Canada and US. The flexural design of flat plate is possible through the Canadian standard S806, using the plane section analysis as in the Canadian standard 23.3, but with adaptation to include the tensile properties of FRB bars instead of steel. Due to lower modulus of elasticity, deflection and crack widths will govern the design. And finally, the bunching shear capacity equation provided by the Canadian standard is recommended for design based on the experimental evidence in many research studies and field applications in North America. Thank you so much for continuing with us till the end.